Hi and welcome back. So this is a question that says draw the most stable conformation for each of the following compounds. Okay, so we can tell right away that this is going to be about chair conformations, right? Chair conformations, because for cyclohexane based compounds, the most stable conformation is going to be the chair conformation, but each of them has two chair conformations, so we're going to draw both of the chair conformations for each compound and then pick the one that's the most stable or the more stable of the two. So let's take a look at the first one. Alright, now molecule number 1. So this structure is the so-called dash and wedge type structure. Okay, dash and wedge structures. And basically, if it's a wedge, that means the substituent on the wedge bond is pointing out from the screen toward us. It's pointing out from the screen toward us. If it's a dashed bond, that means the substituent on that bond is pointing opposite way. It's pointing into the screen, away from us. Into the screen and away from us. So basically, what I would always do for this kind of molecule, before I try and draw out the pair of chair conformations, I would first put it in the planar type structure. That's what I would call it, sort of where I put the ring, I lay the ring down in a plane manner like this, okay, and then draw out the substituents up or down, above or below the ring, the plane of the ring. So for this methyl group, let's put it on this carbon, so it would go up, right, because here it's coming out from the screen and toward us. So if we lay it down, it would go up, whereas this one here would be on the next carbon and going down below the ring, right? And this final methyl group will be on this carbon here, and it's again above the ring. So this is in this structure, we are not distinguishing the one chair conformation from the others. So next, let's try and draw out the two chair conformations based on that. So one of them would be like that, where you have this methyl group on this carbon. Again, it's above the ring, and this one here on next carbon below the ring. And this final methyl group on this carbon here, notice that it's not going straight up. There's no bond that can go that way. Okay, if this carbon atom is going down, it's pointing down like that, then the bond that goes above the ring would go at an angle, right? Would go at an angle rather than straight up. If it's below the ring, it would go straight down. But if it's above the ring, it goes at an angle like that, because this is what we call a E bond, right? Hope you remember that by now. And these two that go straight up and down are A bonds. Okay, so that's one chair conformation. The other one would be opposite, like this. So now these two carbons will be like this one is still above the ring, but it's going at an angle. Remember, if this carbon is going down like this, then the substituent that goes above the ring, goes above this ring, would go at an angle. But if it goes below the ring, then it goes straight down. Okay, So this will be a E bond, but we'll label that later. And this next methyl group is going down, and it's going down at an angle. Why at angles? Because the carbons, all carbons prefer to be in a tetrahedral type of configuration. And we didn't draw out the hydrogen for the sake of simplicity, but the hydrogens for this carbon will be like that. And these 4 bonds will form a tetrahedral structure. That's where the angles come from. So for this carbon, there will be a hydrogen straight up like that. And these 4 bonds form a tetrahedral shape. Okay? So the other methyl group will be here above the ring. This time it will go straight up. Okay, hope that makes sense to you. And now this is the A bond, but both of these will be E bonds. So let's look at the bonds. This conformation have 2 A bonds and 1 E bond. And this one has 1 A bond only, but 2 E bonds. And because the conformation that has the most E bonds will be the more stable conformation, assuming given that these substituents all have similar sizes. And in our case, they're all the same, so of course they have the same size, and so that certainly holds true. The one that contains the largest number of E bonds will be the more stable conformation of the 2. So this is the more stable, or the most stable conformation of this molecule. Okay, so any cyclohexane-based ring structure would always, or most of the time, prefer to be in chair conformations. But which one does it like more? The one it likes more is, the one that has more E bonds. But given that all the substituents from all the bonds have similar sizes, so that's that. Okay, on to the next part. Okay, the second structure. So it's actually kind of similar to structure number 1, except that this substituent was a methyl group for the other one, but here it's C6H5. It is a phenyl group. So whenever you see a C6H5 substituent like that, that means it's a phenyl group or phenyl ring like this. Well, I'm not sure, you may be familiar with it by now, but I'm sure you will learn about it more in the future, later in the class. But the only thing you need to know about it for this question is that it's a big guy. It's very big, much bigger and bulkier compared to the methyl groups. Okay, so that's all we need to know about it. All that matters to it in this question. So anyway, let's try draw out again the what I would call the planar, sort of the planar ring structure first. Let's change colors real quick. Okay. Right? And the methyl group, again, on this carbon, is above the ring. And this neighboring one is below the ring in the opposite direction. And this one, which carbon is the phenyl group on? It's this one, right? C6H5. Okay, that's it. Now let's try and draw the chair. It's not the best chair drawn. Okay, the pair will be like this, and let's use this carbon for the methyl group again, so it's going up the ring straight up, right? Because there's this hydrogen here that will go down at an angle, and these 4 bonds exist in the tetrahedral geometry. Okay, so and this one goes straight down, this other methyl group, and this phenyl group goes up but at an angle. So what happens is, if this carbon goes down, points down like that, then the substituent that goes up would go up at an angle, but the substituent that goes down would go down like this, go straight down, if this carbon here is pointing down like that again. Okay, so this is a hydrogen, so we don't have to draw it out, but the thing is that this bond is at an angle. And okay, that's for that conformation. And in this one, got methyl group up, okay, up at an angle, right? Just like this one. And this methyl group goes down below the ring at an angle again. So if the carbon is pointing up like that, then whatever group that goes down would go down at an angle, whereas any substituent that goes up would go straight up, no angles. In our case, it's a hydrogen that goes up, and we usually just omit that. Okay. And as for the phenyl group, it goes up. This should be in an angle like that. I didn't draw it so well, but this bond is straight up. If it were below the ring, it would go below like an angle, right? Hope you get the idea now. So what happens is, I forgot to mention in the last part of the question, is that any bond that goes above the ring in one conformation also go above the ring in the other conformation. So their position relative to the ring does not change. The same goes for the bonds that go below the ring. If it goes below the ring in one conformation, it does the same thing in the other conformation. So changing the thing from one chair conformation to the other chair conformation only changes the conformation. It doesn't change the configuration, which in this case means the position of the substituents relative to the ring. If it's above, it's still above. If it's below, it's still below, no matter what. So that's a very, very important thing to remember when you try to draw the chair conformations. That's that. So now let's count the bonds. The ones that go straight and up are A bonds. And the ones that go at an angle are E bonds, right? Just to help you remember. So this one, this conformation has 2 A bonds and only 1 E bond. This one has 1 A bond and 2 E bonds, right? What would be the answer? Well, the answer is that this is the more stable conformation, despite the number of A bonds relative to E bonds. It's got only 1 E bond, but because of the size of the phenyl group, it prefers to be in the E bond, no matter what. You know, so even if there's only one E bond, if the E bond carries a really big group compared to the other substituent, then what will happen is that that E bond, the conformation that has the E bond bearing that big group, is the more stable conformation. That's because it helps minimizing the energy of the molecule, minimizing the energy that's created by the steric interaction between the very big group and the other atoms around the ring. So that helps minimizing the interaction. And the energy will be the lowest if the really big group is at an angle like this. That makes it farther apart from the other atoms. That's that. So this is the winning or more stable conformation despite its lower number of the E bond. So that's what happens when you have substituents on the ring that have very, very different sizes compared to each other. Okay, so that's it for part 2. Now on to the next structure. Okay, last one. So let's draw the what I sort of call the planar type structure, which is where the ring exists in a plane, and here we have the OCH3, that's a methoxy group. Okay, and on the third carbon, counting from this carbon here, on the third carbon we have a methyl group that goes down below the ring, and on this carbon we have another group that's going up above the ring. So this is the T-butyl group or T-butyl group. Okay, so as long as you know what it is, it's also a pretty bulky group, pretty big guy. And then chair conformation, let's see. Okay, so now this methoxy group will be on this carbon going straight up, and this methyl group will be on this carbon. Would it go straight down or at an angle? It goes down at an angle, right? And this hydrogen goes straight up, but this substituent goes straight down. Goes down at an angle, because that way this carbon is in a tetrahedral type of configuration. Again, okay. So, and this T-butyl group would be what? Goes up or down? Goes up above the ring. Does it go straight up? Yes, it does go straight up, because there will be a hydrogen that goes down at an angle that creates the tetrahedral type geometry for this carbon. Okay, that's why this guy here goes straight up like that. Okay, that's it for this conformation. And for this one, now this methoxy goes at an angle, okay, and this one, on the other hand, this methyl group goes straight down, and let's see, oh no, this one, sorry, and this one goes up at an angle, CCH3 parenthesis 3. So again, all the E bonds, all the A bonds in one conformation will be E bonds in the other conformation, and same goes for E bonds, which would be A bonds in the other conformation. So let's see, this one has 2 A bonds and only 1 E bond. And this one has 1 A bond, 2 E bond. So this one might be the winner, but wait. Did we consider the size of the substituent? Size of the substituent. Yeah. Actually, this one, the biggest substituent, the most bulky substituent, that's in the E bond. So this one is going to be the favored conformation anyway. So whichever criteria you use for judging the more stable conformation, this one is always going to be the winner because number 1, it's got 2 E bonds. Number 2, the biggest, by far the biggest substituent is on the E bond. So this one is going to be the more stable conformation anyway. Actually, this methoxy group is probably smaller than the T-butyl group, but how much smaller we don't know. We can no longer say that the T-butyl group is far bigger than all the other two. Alright, because now this is a methoxy group and the size of it compared to the T-butyl, how does it compare? We don't quantitatively know that, but it doesn't matter. It doesn't matter because this guy is in the E bond also. So all the substituents that are bigger, all the bigger substituents are in E bonds. So no matter what, this is going to be the lower energy or more stable conformation of the two. Alright. Okay, again, if you have any disagreement or any thoughts or comments or suggestions, anything, just email me or call, or you can subscribe to my channel and leave comments or visit MacroLearning.com. MacroLearning.com. Alright, thank you so much and see you in the next video.